Good morning friends. In today's video, we are going to see some important points related to cooling tower and condensing water design. In the cooling tower, it is an open loop system. That means from the cooling tower, the cold water which will be supplied to the chiller using the condenser water pump. And in the chiller, we have four main components like compressor and condenser, expansion device and evaporator. After the cold water supplied to the condenser, I mean the chiller, this hot water will come back to the cooling tower. So here it will be openly dropped. So that is why it is called as an open loop system. Coming to the closed loop system, in the chiller, we have the chiller here. From the chiller, this cold water which is supplied to the load it can be AHU, FCU and different HVAC equipment used in the building. After the hot return water will come back to the evaporator using the chilled water pump, and at this point it will get the heat condensation, like the heat exchange will happen. So this circuit will be keep on running. In my last video, I explained about how to design the chilled water system in the closed loop system. That means from chiller to this load side. And coming to the open loop system, we normally consider 110 is equal to 3 GPM instead of if you see like in the open closed loop system, that means chiller to building side, we will consider different load like 110 is equal to 1.5 GPM, 110 is equal to 2 GPM, 2.4 GPM like that. But when it comes to open circuit system, that means the chiller to cooling tower, we normally consider 110 is equal to 3 GPM. So in this video, I will explain what is the reason behind this one, and also the refrigeration cycle which we are using for the cooling tower, that will be explained in this video, and also how can we evaluate the cooling tower performance and how cooling towers are rated, and the important parameters in the cooling tower, that is the range and approach and understanding tonnage. So all these points we will explain in detail in this video. So here, as I explained, the load from the the building load will be transferred to the chiller in the evaporator, and from the and at this point in the compressor, the load from the chiller will be transferred to the cooling tower. So here the chilled water system has three parts or stages. That is a condenser water side, that means this side is a open loop side, and the evaporator side, that means the chiller side at this point, and also the load side. Load side, it is the building load side. So coming to the chiller, there are four important things as I explained: compressor, condenser, expansor and evaporator. So here we need to understand the concept of a refrigeration cycle first. So the refrigerant entering the compressor carries the building load. That means the chilled water return temperature at this point. So at this point the load will be there, and at this level we can separate the chiller to two sides. One is the high pressure zone, one is the low pressure zone. So here the refrigerant entering the compressor carries the building BTU or building load. So when it enters the compressor, this refrigeration in the low pressure or low temperature. I mean at this point this will be at a low pressure and low temperature. So this is in the gaseous state. This is not in the liquid state. This is in the gas state. So the compressor pumps up the refrigerant to high pressure and high temperature. So after this compressor portion, so at this point it will be high pressure and high temperature, because the pressure is directly proportional to high temperature. This high pressure and high temperature refrigerant, the gas is passing through the condenser. So at the condenser the heat exchange is happening. So the heat exchange with the cooling tower is happening. So at this point the refrigeration in the form of high pressure high temperature liquid, because of the condensation process happening at this place. So the next step is the expansion device, which reduces the pressure of the liquid refrigerant, and consequently it cools the gases to the liquid. So in the expansion device the area is increased. So when the area is increased, there is a chance of pressure reduction, and also there is a changes of liquid phase of the vapor from the gas to the liquid state at the expansion device point. So at this point it is like a cold liquid state, and this cold liquid refrigerant, it reaches the evaporator. Here again there is a heat transfer is happening. That means the hot water coming from the load, and here the cold water comes from this one chiller. So there is a heat transfer will occur at this point, and because at this point the refrigerant temperature is lower than the return water. So here the point, the temperature is very low, so that's why it takes the heat of the load which is coming in the return side, and the refrigerant heats back up and it evaporates into the low pressure gas, and this cycle is repeated. So again once it takes the heat from the building, again this cycle will be continued like this. And here is the important comparison between cooling tower ton of refrigeration versus evaporator ton or refrigeration ton. So like chillers, cooling towers are rated in terms of tonnage, like 1 ton, 2 ton, like that. Specifically how many BTU per hour they can disperse through the heat of vaporization, or we can say evaporative cooling. So a refrigeration ton is equal to 12,000 BTU per hour, but a cooling tower ton is equal to 15,000 BTU per hour. This extra 3,000 BTU per hour is carried over from the refrigeration cycle. So that one I will explain you how it comes. So when it enters, that means when the refrigerant enters into the compressor, this refrigerant in the low pressure and low temperature gaseous state. That means at this point it will be the load transfer here, and at this point it will be low pressure and low temperature zone. So this compressor which pumps up the refrigerant to a high pressure and high temperature state. So this process requires some energy. Basically adding 3000 BTU power of compressor heat to cooling tower load. That means this comes from the assumption that the compressor generates 3000 BTU per hour in a typical air conditioning application that the cooling tower has to dissipate. So because of this compressor action, we consider that average of 3000 BTU per hour of load is added to the system. That load, the cooling tower must dissipate from the system. So that is the reason the Cooling Tower Institute, or CTI, that's the agency who is responsible for developing the rating system for all the cooling tower, has designated that the cooling tower ton is 15,000 BTU per hour or 12,000 BTU per hour, that is the refrigeration ton, or the chiller ton you can say, plus 3,000 BTU per hour, that is because of the compressor heat. So totally it will be 15,000 BTU per ton for the cooling tower ton, and the evaporator or the refrigeration it will be 12,000 BTU per hour. Because of this additional BTU per hour which comes from the compressor heat, with the open loop system, that means the chiller to cooling tower, that is the open loop system. In the open loop system, GPM capacity is considered as higher compared with the closed loop system. So the next important concept is the cooling tower selection. Let's consider two countries, location A and location B. And in the location A, the ambient temperature is 35 degrees Celsius drivable temperature or 95 degrees Fahrenheit. And location B also same concept. In the location A, the ambient air is less humid. That means more evaporation will happen. That means more heat is being transferred from your body to the outside air because of more evaporation. So coming to the location B, here the drivable temperature is same, but here the ambient air is more humid. So here it is less humid and here it is more humid. That means less evaporation will happen. That means already the air has plenty of moisture compared with the location A. So that means the less heat is being transferred from your body to the outside air, and at this location more heat is transferred from your body to the ambient air, and here less heat is transferred from your body to the ambient air. So in summary, it is harder to evaporate water into air that is already wet. That means the higher the wet bulb, the harder a cooling tower has to work to evaporate enough amount of water to maintain the set point in the system. So that's the main reason cooling tower is working based on the concept of evaporation or evaporatory cooling. It will transfer the heat load through the evaporation. So when you go for the selection of the cooling towers are sized based on the design of wet bulb temperature, not dry bulb temperature of a given region. So different region, the wet bulb temperature is different. We have to consider the wet bulb temperature for the evaporation, because it is the wet bulb temperature that determines how effective they will be at releasing heat into the atmosphere. So what is wet bulb temperature? The wet bulb temperature is the lowest temperature that can be reached under the current ambient condition by the evaporation of water. The actual air temperature, I mean the dry bulb temperature, and the humidity or the amount of moisture in the air determines what is the wet bulb temperature. So in the cyclometry, we can using the two parameters, we can decide the third parameter. So you can use the dry bulb and the humidity or the amount of moisture, then you can decide the wet bulb temperature. Therefore, certain region of the country will differ in the design of wet bulb temperature. For example, you can see the ASHRAE application handbook chapter 14 from 2009 fundamentals, that the wet bulb temperature is different for the different United States region, like Los Angeles 70 degree Fahrenheit, the Vegas it is 71 degree Fahrenheit, and different locations have different wet bulb temperature. So the cooling tower selection must be done based on the wet bulb temperature. How cooling towers are rated? So that is the important thing. The Cooling Tower Institute rates all cooling tower based on the following condition: 95 degree Fahrenheit and 85 degree. That means the 95 degree is the entering point and 85 degree is the leaving point water temperature. And at 78 degree Fahrenheit wet bulb temperature. This is not dry bulb, this is the wet bulb temperature. And 10 degree Fahrenheit range and 7 degree Fahrenheit approach. These two I will explain now. And 3 GPM for cooling tower 10 for the open circuit. Thus, as I explained, this is for the open circuit. We are using 110 is equal to 110 is equal to 3 GPM for the open circuit. So this means 3 GPM of condenser water entering the cooling tower at 95 degree Fahrenheit and leaving the cooling tower at 85 degree Fahrenheit at 78 degree wet bulb temperature. That is the ambient wet bulb temperature. So it is a common operating design condition which puts all the cooling tower on a comparable playing field. So it doesn't mean that, for example, you are in the UAE that as per the Dubai municipality, Dubai Green Building Code, you have to consider like a 46 degree dry bulb and 29 degree wet bulbs condition. So you can ask that that wet bulb I am using for my region is different. So here is the point. It doesn't mean that these are the design conditions that you should use when selecting a cooling tower. So they are very clearly saying that. So this is not the design condition you should use the for your cooling tower. It is important to use the design wet bulb condition for your part of country when making a cooling tower selection. Based on the your country or your region, you have to select the cooling tower considering the local wet bulb temperature. So the value which they rated here is the rated condition, and as they mentioned clearly here, this is the common operating design condition to compare the playing field. So the second important thing, the range and approach. Here I have shown one example. The system flow rate, the chilled water flow rate is 30,000 GPM, and the hot water and cold water. So the hot water means condenser living water temperature. So the water which comes from chiller to the cooling tower. So here we have the cooling tower, here we have the chiller. So water which is coming to the cooling tower. So this living water temperature from the condenser, it is 113 degree Fahrenheit, and condenser entering water temperature. That means after this cooling tower process, the water which is entering into the chiller condenser. So this temperature is 90 degree Fahrenheit. So wet bulb temperature of that particular region, I assume like 78 degree Fahrenheit for that particular location. So the range, the range is equal to HW minus CW. So HW means living water temperature minus entering water temperature. So this is called as a delta T normally. So this is called as a range. So here it is 23 degree Fahrenheit. So coming to the approach, it is CW minus wet bulb. So here these two cases, the entering water temperature minus entering wet bulb temperature. So these two will give you the answer of 12 degree. So this is the approach. So the approach value tell you how close the cooling tower gets the water to the wet bulb temperature of the surrounding air. So this will give you some clear understanding. So wet bulb temperature, the ambient wet bulb temperature, it is 78 degree Fahrenheit. So the cold water from a tower, so tower to the chiller. So after the process, it is 90 degree Fahrenheit, and the difference of these two is called as a approach. Approach, and approach is determined by the size and condition of the cooling tower. Okay, so this parameter is very important to find out the size and condition of the cooling tower. So coming to the next one, and we have the hot water to the tower. So the tower from the chiller, the water which is entering into the cooling tower. So that hot water to the tower. So that is 11 degree Celsius, 113 degree Celsius in our example that we consider. So the difference of these two is called as a cooling range. So this cooling range is determined by the amount of heat load from the process. The process means our overall system. So based on that load, this will be determined, the cooling range. So there will be some changes in the cooling range based on the load of the system. And the next one is the evaporation rate of cooling tower. In the cooling tower, there will be water evaporation will be continuously taking place. So we can find out the evaporation rate of water by using simple formula. Evaporation rate is equal to the flow in GPM. So here the flow rate for the chiller water flow which is coming to the cooling tower, that is 30,000 GPM that I am going to consider here. And delta T, the delta T you can see here, delta T is equal to leaving water temperature minus entering water temperature for the cooling tower. So these two temperature, the difference means these two temperature we have to consider here as a delta T, and 0.1% of evaporation for each 1 degree Fahrenheit. So here the difference you see, it is 23 degree Celsius Fahrenheit. So each 1 degree Fahrenheit we are going to consider the 0.1% as a evaporation rate. So it is 30,000 GPM into these two temperature difference is 113 minus 90, and 0.1 by 100 is equal to 0.001. You have to multiply with this Fahrenheit different temperature in Fahrenheit. So evaporation rate is equal to 690 GPM. So this is the value we can say that this much amount of gallon per minute water is evaporated in the cooling tower. So in this video we discuss what is the range and approach, the important two terms in the cooling tower, and we discuss why the 110 is equal to 3 GPM. I mean the load is higher in the open circuit. So we discuss about the evaporative rate, how to find out the evaporative rate. Also we discuss about the importance, the importance of wet bulb temperature when you select the cooling tower. Then we discuss about how the cooling towers are rated based on the CTI. So these are the important thing you must consider for the selection of the cooling tower as a basic. So thank you for watching the video. We will see you again with another interesting topic.